Thus far in the course, we've previously looked at whether or not alternating series converged. However, other than alternating geometric series, we never really found their actual sums. We don't really have a formula for finding the sums of an alternating series unless we had a common ratio, in which case we could then use what we know about finding sums of geometric series. So the best that we can do is approximate the sum of an alternating series with a clear understanding of its error or how much we are off by. That is to say, in order for us to have a good approximation of a series' sum, we need to have a good sense of what its error is. So I want to start by actually just looking at a basic alternating series. So let me just start with something like this. So n is equal to 1, our upper bound is infinity, and let's say that our alternating series looks something like this. Okay, so let's take a quick look at what this series looks like. We know that our first term here, when n is equal to 1, that means our power here is going to be 2. So that means our first term is positive, and our denominator is simply our n value squared. So this would be 1 over 1 squared, which is just 1. And so now from here, since we know we have an alternator, we're just going to go ahead and write the next term as being negative. And again, our denominator is simply our n value, which this time now is 2 squared. So this would be 1 over 4. And I'm just going to go ahead and just continue to write out my series. Hopefully you get the idea at this point. We have 1 over 25 minus 1 over 36 plus 1 over 49 minus 1 over 64, and so on. So this series is just going to continue. All right, so this is what our alternating series looks like. Again, because this series here, we'll notice, is not a alternating geometric series, we can't simply find the sum. So what we can say, however, are a couple things. Well, we know that this series here, what is listed here in sigma notation, this is our sum. So I'm just going to note that. This is our sum. And we're just going to use the variable s to indicate that this is our sum. And what we have here are the first, I'm just going to arbitrarily choose a first number of terms that we're going to add up. And so we're going to call this here our partial sum. Okay, this is our partial sum, which in this case is just the sum of the first 4 terms, right? So I'm just going to notate this as being s sub 4. So that notation is just saying, hey, we're adding up the first 4 terms in our infinite series. And we're doing this because we can't add up all the terms in an infinite series. That would be impossible. But we're just trying to approximate what we think the actual sum of this series is by adding up an arbitrary number of terms, in this case, 4. So what would make all of this then? This would be what we call our remainder. Okay. And later on, we'll actually call our remainder our error, but we'll get to that. But we're saying here, okay, let's call this R sub 4. Now, I know that might be a little weird or unsettling for some of you, but R sub 4 is simply saying the remainder or the remaining terms after the first 4 terms of this series. Okay, so let's just make sure we understand what we're saying here. We've got our sum. We don't know what our actual sum is, but we know it's equal to our partial sum plus our remainder. Okay, and just for the sake of time here, I'm just going to go ahead and write here what our partial sum is. You could add this on your own. I trust that you can do this, but I'll just write it's 115 over 144. And again, this is equal to R sub 4. All right, so what we're saying is our sum, our actual sum, is equal to our partial sum, which also works as our approximation, plus our remainder, which is how much we are off by. So just to be clear, our remainder here, this is showing how much are we off by is our approximation, 115 over 144. How much is it off by to our actual sum? Now, from here, I want to establish 2 really important facts. Okay, so I'm just going to say 2 things. Right? 2 important things that we need to establish from having looked at this. First off, the first thing I want to establish is that R sub 4 here must be greater than 0. Or in other words, R sub 4, our remainder, has to be positive. And take a moment and think about why this has to be the case. How do you know for certain that a remainder has to be positive? So if you need to pause it, you can, but just think about that for a moment. Well, hopefully you've had an opportunity to think about that. And one way of maybe kind of viewing our remainder is to see it as the difference of a bunch of pairs of numbers. For example, here, look at the way I've just paired it. I've noticed I have 1 over 25 minus 1 over 36. I'm taking a value and I'm subtracting from it a smaller value. I know it's smaller because my numerator is the same, but my denominator is larger. So I'm subtracting a larger denominator, which makes the whole ratio smaller. In other words, this difference is going to be positive. And I know that this next difference is going to be positive, and so on and so forth. So a remainder consists of the sum of a bunch of positive differences. Therefore, I know my remainder has to be positive. Remainder is positive, okay? Now, next thing. The next thing I can establish from looking at this series here is that I know that my remainder, r sub 4, has to be less than 1 over 25, right? So let me clear this out of the way so you can see that. What I'm saying here is that our remainder has to be less than this value. And again, I encourage you to think about why this has to be the case. So pause it if you need to. Well, if you had a chance to think about it, hopefully you see one way of thinking about this is to look at the terms after 1 over 25. So I'm going to group together 1 over 36 over 1 over 49, in which case, since I'm putting parentheses or grouping around that, I'm going to say that this is going to be minus 1 over 49. And in order for this to all work, I actually need one more term here, so you can see that. So I'm going to say this is plus, what was that, 1 over 81, since it's 9 squared. So again, to group that together, and put that and make this term negative, well, think about what's happening here. I am subtracting, again, this entire grouping, 1 over 36 minus 1 over 49, all of this is going to be positive. All of this is going to be positive. So I'm subtracting a bunch of positive values from 1 over 25. So what does that mean? It means my entire remainder is getting smaller because I start with 1 over 25. That's the first term in my remainder, but I'm subtracting a bunch of smaller values, okay, or positive values, I should say. And so that means my remainder is getting smaller and smaller and smaller. Its sum is getting smaller. But because I established in my first thing, or my first fact, that my remainder is positive, I know that while it gets smaller, it never dips below 0. It stays positive. So I'm able to state pretty definitively here that I know for certain that my remainder here, r sub 4, is less than 1 over 25, right? So from here, this gives us a good sense of what our bounds for our remainder must be. So kind of borrowing from this line here, I can then say the following. I can say, all right, if I take this fact here, and now keep in mind the two things that we just established, I can then say the following. I know that the sum, my actual sum of my series, I do know that it is greater than S sub 4. I know it's greater than my partial sum. Okay, and I'll actually write the actual value underneath. So it's greater than 115 over 144. I know that for certain. And because again, my remainder is positive, right? And I can then say that my R sub 4, or my sum, I should say, is less than my partial sum plus whatever our next unused term is, I should say. It's less than my partial sum plus a sub n plus 1, right? And so this is just me describing let me get this out of the way, the next unused term. So in this case, I would say it's less than 115 over 144 plus, what was my next unused term? That was 1 over 25. Okay. So to put this plainly, we can say that our remainder, or our error of our approximate sum, is, summarize, and I'll just write this. To summarize, basically what we're saying here is the following. We can say that 1, the absolute value, and I'll talk about why we're using absolute value in a bit, but the absolute value of our sum minus our partial sum. In other words, how much is our partial sum, or approximation, off by our actual sum? That is our remainder, or our error. And we can then say that this remainder, or this error, how much we are off by, has to be less than or equal to a sub n plus 1. And we've got two kind of an equation and an inequality. If I put it all together here, I could say, just kind of summarize this as the absolute value of our remainder is equal to the difference between our sum and our partial sum. It's how much we are off by, but we know that this error has to be less than or equal to a sub n plus 1. So this here gives us our lower bound, and this here represents our upper bound. To put this really simply into words, what we're effectively saying is the following. For an alternating series, I can approximate an alternating series' sum by looking at some partial sum. Obviously, the more terms that we have, the better our approximation is going to be. Our error is simply our remainder. It's how much our partial sum is off by. Our remainder says how much we are off by. What the alternating series error bound theorem simply states is that this remainder, our error, must be less than our first unused term, or in other words, the first term that we are not adding as part of our partial sum. It's as simple as that. Now, you'll notice that I talked about the absolute value here. Why am I mentioning absolute value? Well, if you go back to my original series, notice that I quote unquote arbitrarily stopped at the first 4 terms. But what if I had actually had you say, let's add the first 5 terms of this series? What if I said my partial sum was going to be consisting of the first 5 terms? Well, in this case now, my first unused term would be a negative value. So what then? Well, we can still establish the same 2 things, or similar 2 things, but now our inequality is simply flipped around. But that doesn't change the alternating series error-bound theorem. It simply says that, okay, if I said my partial sum consisted of the first 5 terms in the series, then I can say that my remainder must be less than, my remainder, r sub 5 now, would have to be less than my first unused term, which in this case would be 1 over 36, must be less than that value, right? Or I should say less than or equal to the absolute value of negative 1 over 36. And so that doesn't change. So over the course of the next couple of problems, or in the rest of this lesson, we're going to be looking at approximating the value or the sum of alternating series, and also getting a sense of how good that approximation is by looking at its error.